Researchers took a language model and they just removed 77% of its main processing parts. I mean, that's like taking out 3/4 of its brain. The obvious question is, how could it possibly still work, let alone work better? Seriously, how is that even possible? Let's figure it out.
You know the drill in the AI world for the past few years? The race has been all about one thing: building the biggest model possible. More parameters, more data, more computing power. And look, it's led to some amazing breakthroughs for sure, but it's also created these absolute monsters, these giant energy-guzzling models that are insanely expensive to build and run. It puts them way out of reach for most people.
Okay, check this out, because this is where it gets really interesting. A typical AI network is what we call dense. Almost every part is connected to every other part in the next layer. It's just a wall of connections. But our brains, they're the complete opposite. They are incredibly sparse.
And that leads us to this really important idea: over-parameterization. It's basically the theory that our current AI models are just bloated. They're packed with all these extra connections that aren't really doing anything useful. They're carrying around a ton of dead weight. So this research decided to find out what would happen if you just trimmed all that fat.
Now here's the kicker. The technique they used to do this radical AI liposuction, it wasn't even new. They cleverly stole it from a completely different part of the AI world: computer vision. You know, the part of AI that teaches computers how to see.
So here's the big aha moment. The researchers realized that those dense, chunky layers that make up most of a language model are, mathematically speaking, the exact same thing as a special operation used to process images. And this was huge because it meant a trick that was already proven to make image models way more efficient could, in theory, be used on a language model.
So how does this actually work? Well, instead of one massive, inefficient calculation, this technique is way smarter. It breaks the problem down. It splits the data into smaller groups, processes each one on its own with way fewer connections, and then cleverly stitches the results back together. It's kind of like replacing one giant, pointless meeting at work with a few small, focused groups that actually get stuff done. The result is you get the same job done, but with a tiny fraction of the resources.
Now, this all sounds great on paper, but, does it actually work in practice? So the researchers trained up their new slimmed-down model and put it head-to-head with the original, bigger version. And the results? Well, they were definitely not what anyone expected. Just take a look at this table. The original model on top has 227 million parameters. Now look at the second one, the optimized one. It's got just 35 million. That's only 15% of the original, and its performance score, that validation loss number, is almost identical. But then, get this, the third row. This is the real shocker. With only 53 million parameters, so still 77% smaller than the original, this model actually performed better than the big one.
And this chart just lays it out, plain and simple. The optimized model, the one with 77% fewer parts, didn't just manage to keep up. It actually won. It learned more effectively. It's like by forcing the AI into a smaller space, you're actually forcing it to get smarter and find the real patterns instead of just memorizing things. So what is the big takeaway from all of this? This isn't just some clever little engineering trick. This could point to a really fundamental shift in how we think about building AI in the future.
This matters for a few huge reasons. First, it proves that a smarter design can actually beat raw size. Second, it suggests that giving an AI constraints, boxing it in a little, can actually make it learn better. And this last one, this is huge. This makes powerful AI way more accessible. The researchers ran these entire experiments on a single normal gaming GPU in under 3 days. That opens the door for so many more people to experiment and contribute to AI.
And that really leaves us with this final thought, doesn't it? For so long, the answer to making better AI has just been more. More data, more compute, more parameters. But this research points down a totally different path. Maybe the future of AI isn't about building bigger brains, but about designing much, much smarter ones.